My name's, for I don't remember, is Duncan. I'm with RJC. We practice in the building science restoration field, and we do structural consulting. What I'm looking at here in this study, in this presentation, is about those glass condos and what we can do maybe in the future to improve their energy performance. It's really focused on the energy performance of the wall, not as much the HVAC. So whereas Ted's talk was very broad about the entire thing, this will be more focused on the wall system itself thermally. So we would say, our overview, why would we bother with retrofitting glass towers? As many of us are aware, climate change is becoming more and more of an issue. Energy consumption, especially in the residential area, is rising, and it needs to be controlled. If we look at Toronto itself, there's lots of glass towers going up, which don't have the best R value compared to punch window systems. So they're around an R2, maybe R3, and hard to get much higher than that. And the thing that everyone always talks about is there's so much glass on all of our Toronto condos. We took we have a methodology to our approach to how we looked at these feasibility studies. We looked at using different materials on an existing building to improve its performance. We looked at using spray foam, so sort of a two-component, what was called earlier a medium density spray foam, so 2 pounds per cubic foot. Adding an interior insulation, which would be sort of the blue or pink board, so extruded polystyrene insulation, and also VIP, so vacuum insulated panels. So the first two chew up some of our interior space, that's why we thought looking at a VIP panel would be more interesting, because we would keep that space and see how a VIP panel system would work on these condos. So there's the spray foam block, exterior or interior insulation, so that's pink, that's the pink extruded board. And then we have the VIP panel. So for those who aren't familiar with the VIP technology, it's they vacuum insulate a silica core around with this nice little, very robust foil bag on it. So that keeps a vacuum in it, which has a very high insulating value. The problem with a lot of the VIPS technology, the new technologies, it's quite delicate in construction terms. You can't really bend this. If you puncture it, it loses its vacuum. So how they're typically handled is they're encapsulated in a spandrel panel. So there's 2 pieces of glass on each side, and that's how we protect it. So it would go in as a spandrel unit into an existing glass. We did a lot of therm modeling, so we have some base cases and then all the different models, and I'll show you all the fancy modeling pictures of them all and all the numbers. And we got a bunch of results, and we'll discuss sort of what we found and where we think some feasible options are going forward. So as we can see, the residential portion of that graph is 15 to 17%, 17% energy use, so it's almost 20%. So 1/5 of our energy is spent in residential uses, and about 15% of our greenhouse gas emissions. That's from 2009. So it's a big part of the pie, maybe not as much as transportation, some would say, but it's something that we can focus on every day, and if we change it as a passive system, it makes a big difference overall in our energy footprint. So some of these numbers are from a couple months ago, but out of the 116 out of the 130 towers are residential in Toronto right now, which is around 90% of them. So if you think about it, if 90% of these towers were all improved, that would be a very big difference in our overall energy bill and the thermal comfort of the people. Majority of these use a window wall system, which is a very high window to wall ratio. The service life of the exterior cladding system is different than the structure itself. So the structures we've designed to 50 to 100 years. The cladding systems sometimes get around 20 to 30 years. It's hard to get beyond 30, I would say, for a newer building for a cladding system. 20 would be like it. But what people are always looking for on these residential ones appears to be a lower initial cost, which is quick to install, but replacement becomes quite expensive. So it goes back to the life cycle costing Ted was talking about. So we'll take questions at the end. Sorry. So the clarification is that The glass IGU units may last 20 years. When I say the windows, yeah, it would be the IGU unit, but we also want the performance of the overall system, the framing system, to last a long time. So that includes the moisture performance, air performance, thermal, and vapor control. So those should last on a similar cycle as the glass, is what we would say. We don't want just the glass to last 20 years. We want all of those layers to last. Some other background is, as I'm sure some of you are aware, there's a thing called the Toronto Tower Renewal Program. That's where, so Ted has done some work, and other consultants in the field, and a lot of suppliers. There's a lot of older, the MERB buildings. They have good bones, but they need to be rehabbed. They have sound structures, poor enclosures, and this philosophy we're looking at really is what we're looking at when we think of this feasibility study, is what would there be? Would there be a glass tower renewal program maybe sometime in the future? Because we're thinking that these are going to happen as it comes through in the coming decades. These buildings will need to be retrofitted eventually, and this is sort of just the beginning look at it. It doesn't put us on any particular pathway, but it's an interesting start to the discussion of something we'll have to do maybe in 20 or 30 years. So what are the minimum values we're working at right now? So in climate zones 5 and 6, which covers a lot of Ontario, or at least the southern portion of it, we get 0.31 watts per meter squared Kelvin. So that's our wall, and then our window is 2.56. So our wall is much higher. We consider a much higher performance for our wall. So windows is only 12%. But on larger, these residential buildings, where they're mostly window wall, that 12% is everywhere. So we have a much lower performance thermally. So we want to make sure that what we put on there will work, and if it's not working, we have to fix it. So in a perfect world, this is my engineering architecture building. It's ugly as sin. It's very simple construction geometry. It's a box, which is great for me. UV, wind, and bomb resistant, and spray walls with spray foam with a really high insulating value. So that's what I would love my house to look like, but I'm married, so I'm not allowed to have it look like that. It has much more windows than my calculations would say is good. So this is a graph from John Straub's book. So we can see he's put our window wall ratios on the bottom. We have effective overall wall value. So we think a typical curtain wall is this yellow band here. That's our commercial enclosure range. And here's where our high performance buildings would be. So ideally, he's sort of saying if you're around 40 in your commercial enclosure, you're here with sort of glass, good glass somewhere up there. And this is something where we're getting a higher performing building where we've got very good wall, like R30 effective, and very well thermally broken systems, and a very good window system put in there. If we have a low window-to-wall ratio, we don't have enough daylight. People say that. So we like to get somewhere around 40. As it gets more and more window added, we tend to lose the ability to control solar as effectively, solar and thermal. So we have thermal comfort issues. The repair strategies we looked at, as I said previously, we looked at spray-applied polyurethane foam. As we saw earlier, it's a foaming agent and a resin. In our case, we're considering it to act as a thermal, air, and vapor control layer all in one. We're going to go with the high-density one, or medium density it's called. And to install it, just to be clear, it does require proprietary equipment and personal protective PPE. And in these applications, we'd be doing it inside sort of occupied units. So that becomes something we need to consider. We had vacuum insulated panels, so silica sore, vacuum sealed. We sandwich it between the glass, as we can see on the bottom here. So it essentially becomes a spandrel unit. So that's why the core bag is prone to damage and poor long-term durability. So we have to protect it. So to make it more expensive, not already expensive enough, you have to put it in glass. And finally, we have extruded polystyrene insulation. commonly found. We can use it outside, we can use it inside, and it's obviously made as a plastic. These are all extruded boards, so not expanded, not the bead board. So what are the performance of these things separated? We have the spray foam, which is about 5 to 6. VIP, which is really high, which is 23 R per inch, which is pretty amazing. This is the space age technology. And then we have our XPS is somewhere around 5. So these are average values we would find comparing different products. And these are what were put into the modeling. So the geometry of what we're modeling, we modeled one bay. Actually, we measured, one of our junior engineers lives in a glass condo, so we measured up his window system just to make sure we were very accurate. And it's 3 feet between the mullions and 8 feet high. So we have the sill, jam, head, intermediate, and that's the geometry of what we're using. When we rough out the measurements, it was sort of, the middle area here is about 50% of these two areas, is what we found on it. So that's what we've kept. So this area in the middle is 50% of the other two. So there's four main cases we looked at. A base case, so just what it is right now, so that's the 3 panel. We did case 1, where we added 5 inches of spray foam to the inside of the top and bottom, and then studs in a drywall finish, because no one likes to look at the spray foam. We have case 2, where we modified it and did rigid insulation and an interior drywall finish. And then case 3, where we had the VIP panel, instead of doing interior finishes. We switched out just the glass panel on the top and bottom. Our baseline parameters are pretty standard. We would do for modeling in Toronto. So minus 18 exterior, 21 interior. We had the aluminum frame they were using, and a 25 millimeter IGU. So this is what the base case looks like. As you can see, it's a piece of glass. That's what we get in window wall systems. This is just in the field, so there are also ones showing the framing as well. So that's our exterior and interior. Case 1 is with our spray foam. So we added the 5 inches of spray foam, and then we have the stud held back with some airspace here, and then our interior gypsum board. Case 2, so we added interior rigid insulation. So there's a gap here because we have to make up that mullion depth. We're not stuffing it tight against the window. We left that there and held it back a bit. So it's continuous over the area. And then we have this steel stud and then a drywall frame. And then case 3 looks a lot like case 1, except it's a vacuum insulated panel. So it's opaque and it's got our fancy little technology inside it. So I'm going to go through a couple of the modeling results, and we can see the difference between them. So here's our base case, head and sill model. So this is just what it looks like when it's built. So from day 1 until you do a retrofit. So we've got the floor slab, concrete floor slab here. There's a spandrel panel over here, and our window wall system comes down here. We've got, as you can see, these are the thermal isotherms. So you can see that sort of on the inside here, we've got a colder area. So it's about 5 to 6 Celsius, which at 21 C is getting us to sort of a moderate condensation risk. And we've got similar performance at the sill. So you can see, for those of you who don't look at therm models all the time, when we see all the lines here, the lines close together, that means this piece of insulation is doing the bulk of the work for resisting our thermal passage. And you can see they all sort of come up and line up again in the window. You can see where it bunches up here. That's doing all the work. But here in the window, that's to do all the work, and they see them all in the middle in the airspace. So you can see here's that condensation area lined up. And this is what it looks like when you flip to the infrared scan on it. You can see it's quite cool on the interior, so there's sort of a moderate condensation risk there. And so whenever we run therm models, sometimes it always, even under walls and windows we know are working in practice. We say, oh yeah, that looks like it could condense there. People say, oh, well, it's not condensing now. I say, yes, that's because this model is run at steady state, but assumes the true temperatures and lets everything run to equilibrium. But in practice, we have forced air running or some heaters, and so we're washing that air with hot air to make sure we're moving away that moisture and it's getting rejected somewhere else. So this is what it looks like right now. So you can see we've got some cold spots on it, and we're looking to improve that. So this is the base case looking at the jam. This is sort of our typical jam. Again, we have everything taken up, a lot of thermal bridging there. You can see how everything sort of comes down to that little green thermal break. That's doing a lot of work there, a lot more maybe than it needs to. So what did we find? We found sill and head. We had interior surface of 7 at the slab, 5, 6 at the head sill, which, that gives us some condensation potential, but it's something that may be able to be managed. Typically is managed through mechanical means. And at the jam, we have about 10 C available, which is much higher. It's much better. So if we look at the first case, we've got, again, 5 inches spray foam here and there with steel stud and drywall put on. So we've taken the window wall ratio from 100% in this one module down to 50%. So we're cutting it in half. So remember that graph, we're moving down on it. We're trying to move into the good range that shows on the graph. This is what it looks like in the model. See, we've sprayed up tight to the glass. Yes, there may be constructability issues with this, so we'll talk about that at the end. This is just looking at a feasibility study. So we foam it all up there. We have our stud here with our drywall. And you can see, remember all those lines are up here? Now they're all moving into this range. So the spray foam is taking up all that thermal work now. We're not letting the window do much anymore. It's all happening here on the isotherms. And similarly, we can see here all these sort of flow in up this way. So we're letting that spray foam take over that thermal insulation work. Yes, we're blocking the window, but we're trying to let the spray foam do the work. And then on the intermediate, we obviously have to change the condition. We can't have it just stop. We have to finish with a trim. So we come here, we get, pretty cold spot right there. It's about 2 degrees Celsius, which is something that has to be looked at in feasibility, right? We're getting 1 degree Celsius right below the trim because it's getting very cold there, right at that zone. So how do we look? When we look at this, we can see it's very, very warm on the inside now that we've had all the spray foam, and now we get this transition zone where it gets very, very cold. And I don't know if we're able to deal with a 1 degree difference with a mechanical ventilation. So this sets up microclimates all over the building then. We have to control condensation. So it's good to pick these up in feasibility studies as opposed to after you build it, is what we would say. And so it's interesting to find that we are trying to fix a problem, but we don't want to make problems as we're fixing them. And this is what the jam looks like. You can see where all the isotherms, we used to be taking all the flux here, now it's all coming back here. So what did that get us? So we got an interior surface temperature of 18 now at the drywall, 10 at the slab. And we're getting some condensation potential at the intermediate where we didn't have it before. So the intermediate used to be an okay spot, but now it's gotten sort of worse by adding it. And then on the stud on the back on the inside, we don't get any condensation potential. It's 18C. And so you should remember that the spray foam, the water wouldn't condense as much inside it because it's not allowing that flow. So we had interior insulation. Very similar makeup to the spray foam, but a little different because we've got this big air cavity we're leaving here, and we're adding the rigid insulation on the back side of the framing, of the mullion framing. So this obviously leaves a risk that we have this airspace in here that we have to somehow encapsulate from the remainder of the interior. But we let the model run because we wanted to see what would happen thermally. So again, you're seeing all of the isotherms move to that insulation layer. We're taking it away from the glass to a similar degree to the spray foam. Maybe not as much, but a similar degree. Again, you see here we have the intermediate. This is at the sill condition. Looking at it, we can see we've again got that condensation zone there where we're getting quite cold very close to the glass because we're adding insulation on the inside. So looking at the jam, We can see it's added in here. We have our space there. But you can see it's sort of -9 here in this airspace. So if you think of the winter, we have -9 in here. If there's any moisture in there, that might lead to a lot of issues. So it's something that would need to be addressed. So we have -7 at the head and sill frame interface. This is a very high condensation potential if air leakage is not managed. So not just in the winter, but also the shoulder seasons. This sort of system would have to be managed. If it's not done right, it could lead to a lot of concealed issues. The intermediate, similar to the spray foam, we might get some condensation potential. And the jam at the back, we're getting 15 to 18, so there's no potential really there. The VIP panels, so you can see it's 613, roughly 613.6 is the size of the unit, and it just goes in at the bottom and top, and it's now opaque, so it's blocking all the vision. It would look very similar to sort of a commercial over the slab edge spandrel panel. So here, it looks the same as a base case. All we've done is just replace out that unit. And again, we're still getting a similar condensation risk we had on the base case on it. But one thing that you do note, from the base case, you didn't see this red on the back. So that shows that it's much warmer on the inside. That shows that the major thermal difference between the two units, between using a glass and a VIP. So it's getting much better performance in the field. But again, if we're not changing the framing, we may not get the full effect of that VIP panel, because it may be very good in the field, but the aluminum framing thermal bridging may counteract a lot of that. So this is what it looks like at the intermediates and jams. We would see it would look very similar, so it's a pretty straightforward install. And you can see the interior surface is much higher. We get 10 at the slab, 7 at the head, 11 at the jam, so some improvement, but it looks, we're getting similar numbers to sort of a window system. So if we take all that, turn it into numbers, what are we actually getting? We're getting the base case up here on the top. There's my pointer there. The base case is about 2 across. Base case gives us about 2.6. So we take all of these. These are all the lower panel, middle, upper, glass center of panel, retrofit center of panel. And these are our actual values we're getting. So 2.6, 4.7, 4.4, 3.3. So we've retrofitted, we've added loads of spray foam, we've added interior insulation, we added VIPs to the center, and we're getting better than 2.6, but we're not getting 20, we're not getting 30, we're not even getting 15. We're still below 5 on a one module basis. So we can see that spray foam is giving us the most at 4.7, so it's a little less than doubling it. And that's, if you look at our center panel number, that's 32.6. So you can see at 32 spray foam, the thermal bridging effects almost totally override what we're trying to do to help them. And this, as we could all imagine, would not be a cheap project to do on a 20-story high-rise. So we have to make sure that what we're doing makes sense. Just looking at the center panel, our base case is here, the little tiny one over here. But when we look at the retrofit one, we can see much improved performance. So this is really showing us that we can improve the middle of it a lot. We can add a lot of stuff to it. But is it really changing what we're getting on it? And unfortunately, due to the thermal bridging, we're not able to overcome that even when we add stuff on the inside, because the aluminum is such a good conductor. The total effective R value of the cases, we can see the baseline over here. And then spray foam and XPS are quite similar, actually. And there's about 75 millimeters of difference between them. And there's probably a major cost difference between them. So there's definitely more study could be done on making one of them work better or more effectively. And the VIP, I thought when we first did this study a couple months ago, I thought the VIP would be a bit better. Maybe I was swayed in by some marketing. But it's better than the base case. But I don't know if we could justify it long term because it is quite an expensive material. Maybe they should add it in the beginning, just for fun. So what does VIP have? It has the highest thermal performance, sort of as a one-component piece. But it has the greatest edge effects because it's not accommodating, it's not able to address those existing thermal bridge effects. The VIP can't do anything about that. You can't field cut a vacuum insulated panel because it's glass and a spandrel panel. So we need to be carefully manufactured. We have to check that everything has to be pre-sized, pre-manufactured before getting to site. A benefit though, especially on these residential ones, there's no loss of interior space. I don't know how well people use this space against their windows. Whenever I go to visit my friends in condos, there's just couches pushed up against them, so maybe no one will care. But it's also an expensive material cost. I think we roughed it out at around $900 per bay. So we rough it out as about $1,000 per bay. If you have, maybe 10 of those a unit, that's $10,000. It adds up pretty quickly. And that's just to take out and install a fancy piece of glass, which gives you marginal benefit over what was there existing. The spray foam, we get the best thermal performance, 4.7 versus 2.6, that's still better. We get less edge effects, except at the intermediates, where, I don't remember, you saw that it gets down to 1 degree Celsius. That's a very high condensation potential, and that's something that needs to be addressed. The edge effects aren't, well, we can mitigate them in some areas, we can't do it in all areas. We need special equipment to do it. It'd be very interesting to do it in an occupied building. We may have to move people out. There's definitely fumes. I think when we do it, if you do it in a house, you have to leave the house for 24, 48 hours to let all the fumes dissipate on it. So there's definitely things to work on it. It does act as the air vapor control layer, so we encapsulate that whole window. So we're blocking thermal as well. If you think about it, if you did this without doing some pre-treatment to the back of the window, you would just see spray foam against your vision piece, which obviously something might have to be done about that because it'll look like spray foam up against a piece of glass, and that might not be the best architectural look. I'm not an architect, so I don't know if that's a good idea or not. But it does act as our air vapor control layer, so it does help us improve the air tightness. So we'll get some improvement on it, and it'll help mitigate definitely vapor control, any vapor issues. We do lose interior space, and it's difficult to access the existing glazing. And we talked with some people. We think we can get a per module cost down to about $450 per bay, which is half the price of a VIP. But it's still pretty expensive. We do lose interior space. So it actually triggers, bylaws and condominiums where we're losing interior space. It could be quite a big legal fight to get through it. If, say, half the building wants to and half doesn't, you may not be able to do it in a building. If we just add a rigid board, it seems the most straightforward option. You can lug the boards up through an elevator without much issue. It's pretty conventional, pretty straightforward. It has a very, very large risk with an air cavity condensation potential between the glass and insulation. Even though we would be able to access that and seal it, the question is how long will that seal last long term? We don't want to put a time bomb in that will cause problems down the road. Again, we lose interior space when we add it to the inside. It's difficult to access the existing glazing, but it's also the cheapest option, which I think maybe is why more study could be done in this area to see how it improves. It's more cost effective than doing the spray foam, but we can see as we keep adding insulation, we don't seem to get a straightforward linear relationship between adding insulation and getting benefit. There's a diminishing return we're running into here due to the existing framing, thermally bridging everything. So here's that graph again we saw from Straub. You see our baseline case is way over here with a little star. And then everything else sort of ends up here. So we have the yellow circle is our VIP, the green triangle is the interior rigid, and then the blue diamond almost interfacing with the triangle is our spray foam. So we moved from this area, which is sort of one we consider in the bad end, towards the good end of the graph. We're really trying to move up to this high-performance enclosure. And we're getting there by adding it. Are we getting there enough? I guess that's further study. We could say what we would do to the mechanical, electrical systems, lighting systems. If we add this stuff, there might have to be changes there as well. We would think that the spray foam, just based off numbers, at this point, appears to be the best option based off thermal performance. It doesn't have that condensation potential problem, and it's sort of in the mid-range on material availability and cost. There's definitely constructability issues we'd have to look at further, but I think as a first step, it's sort of maybe a path to go forward on, and I'm sure we'll have some discussion about what might be a better one. This gives us, we would call preliminary analysis of the likely energy performance of existing residential building stock in Toronto. We work on a lot of these high-rise towers now, doing some repairs to them. No one's really looked at this point of how to deal with, at the 20-year mark, even though the reserve funds go over 30, what they're going to do. There's items in there. We have worked on one where it said we're going to tear all the curtain wall down, or all the window wall down, and put up a new curtain wall in 20 years, which is the most aggressive one I've seen yet. But as far as this goes, maybe in the future there'll be a glass tower renewal guideline. It may come to that. There are a couple hundred of these buildings around, so it might be worthwhile to make a best practice guide. And definitely further studies required to accurately understand the performance, constructability of these retrofits, look at different systems, look at different spacing of the modules, maybe even do a mock-up with some of the project partners in Toronto. So that's my conclusion, because it's all numbers. Thank you very much.